Hello, everyone. Thanks for tuning in. My name is David. I am teaching mathematics and statistics in Ingolstadt in Germany. And today I want to talk about something we all deal with every day now, generative AI. More specifically, I want to look at how it fits into our world of data analysis and why, despite all the automation, the human factor is still the most important part of the equation. I want to start with a little trip down memory lane. This is me exactly 7 years ago at the Discovery Summit in Copenhagen. I was giving a talk on solving classification problems with deep learning, where it's hard to believe that this is already 7 years ago, but I show it because looking back, it seems like we were quite clueless. I was, at least. We thought we were at the cutting edge of AI, watching programs like AlphaGo play Go at a superhuman level. But we had no idea at that time how generative AI would explode and change almost every aspect of our lives by 26. Back then, we were happy if a neural network could tell a cat from a dog. And today it's writing code, it's helping us diagnose cancer, and maybe, let's see, it's doing our statistical analysis. Here's the plan for today. I'll start with part one, a bit of history to put the question in perspective. Then in part two, I show the design of the study. And after that, I go to JMP to demo some results. And we'll wrap up with some conclusions in the final part. Okay, so let's start and dive into part one, the historic perspective. The title of my talk is Data Analysis, Generative AI, and the Human Factor. But in fact, a simpler version of it would simply be, is generative AI finally going to take over statistics? Are we, as data scientists and statisticians, finally about to become obsolete? Now, let's start with some good news, if you want, why generative AI could work in the context of data analysis. If you need to prove to someone or to something that you're human, the most typical task is a captcha, reading some distorted numbers or letters from your screen. And why is that? Because human vision is remarkably robust, something called perceptual constancy. And that is absolutely not the case for AI. AI algorithms have tremendous difficulties recognizing a chair if, for example, it's upside down, or a cow, as you can see in the bottom right, that is on the beach. If you're interested in more examples and details about these differences between human intelligence and artificial intelligence, you can find a talk I gave on that subject in the JMP community, and I leave you the link here. But the good news is the following. These typical weaknesses that we can observe in AI, they are irrelevant for data analysis, right? There's no shadow or weird angle or any other distraction in a spreadsheet. Now, before we all get too excited, let's look at how good we generally are in predicting the future. So in German, there's a nice saying, predictions tend to be difficult, especially when they concern the future. So in 2015, Elon Musk said we have fully autonomous cars in 2 years. 1 year later, 2016, the AI legend and Nobel laureate Geoffrey Hinton said we should stop training radiologists because AI would replace them within 5 years. And here's a picture of radiologists driving to work. Radiologists are still very much employed, despite the fact that AI is playing a big role in their field. So every few years, a new technology arrives promising to automate insights. And every time someone stands up and says statistics is finally obsolete. So let's have a look at some examples. The first example that I remember, the first wave was in the 90s with the rise of what was called data mining at that time. So computers were getting very powerful, and the sentiment was that we could just brute force pattern. Why bother with statistical theory? We can just directly dig into the data. So this led actually to some tension between the different communities, famously summarized by one statistician saying data mining is a dirty word in statistics. The belief was, why model when you can just search? And as you all know, statistics survived. 10 years later, we had the big data movement gaining some momentum. And there, once again, the argument was simple. When you have terabytes of data, sampling error vanishes and we can just rely on correlation. The Wired magazine published a famous article from Chris Anderson titled "The End of Theory." We can stop looking for models. Correlation is enough. And once again, statistics survived that. In 2012, roughly, deep learning was supposed to kill human feature engineering. And there's no doubt the rise of multi-layered deep learning networks advanced the field of pattern recognition and computer vision in an unprecedented way. But as we all know, it came with some very serious issues. And to detect these issues, to describe them, and to try to mitigate them, what do we use? Classic statistical methods. Which brings us to today's era. The new prediction is that generative AI makes technical skills obsolete. The famous quote in this context is from the CEO of NVIDIA, Jensen Huang, who recently said the following: everyone is a programmer now. You can just say to the computer what you want. So here's the big question. Is this true for statistics as well? Can we say everyone is a statistician now? You can just say to the computer what you want. Well, that's exactly what we are going to put to the test. Now, before we jump to the results, let's look at the design of the study. To me, it was clear from the beginning, unfortunately, that I couldn't make a very comprehensive study. I had to make a lot of choices to keep the scope manageable. The first choice I had to make was which generative AI to use. You see some options on this slide, and I ended up opting for Gemini, mostly because of three reasons. The first one, it's free to use. The second one is that over the last 10, 15 years, I have been quite impressed by the contributions of Google and DeepMind, like, for example, AlphaGo, the transformer technology, which is the core of every large language model, or the publication of AlphaFold. And the third reason is that I made some preliminary tests, and Gemini showed strong results. So this is why I'm going to use Gemini in my study. Then I also had to decide what level of statistical knowledge I would assume the user had, or in other words, how much statistical detail I would include in the prompts. On the slide, you see three different versions. The first one with expert level, with a lot of details in the prompt. The second one with some solid statistical knowledge, roughly at student level. And the third one that has no statistical knowledge at all. And I decided to use the third version, the zero knowledge version, because if you remember, our initial hypothesis was that everybody is a statistician now, so no stats knowledge is needed. Also, I needed to make a choice of problems to solve, and I decided to test 5 different areas: descriptive statistics, hypothesis testing, linear models, classification, and design of experiments. And in every field, I chose one relatively straightforward example and one that contained at least one difficulty, one non-standard issue, like an assumption for a test that was not met, or in the case of design of experiment, a constraint, for example. And finally, I had to make a choice of data sets as well that represent the corresponding areas that I wanted to test. All right, enough with the slides. So let's see what actually happened. So I'm switching to JMP now. So here's my JMP journal, and I would like to start by giving you an impression of 3 different ways how you can generate your analysis. So the first version is the classic one. You use JMP and you work with menus. So I have a small data set here that just contains 2 variables, a country and a weight. So if we look at the distribution, you can see that I have 3 different countries here: Germany, Japan, and the US. And we have 87 cars here in this data set, and their weight is recorded. And obviously, one fundamental question that we can ask is if the mean weight within these 3 countries or between these 3 countries is different. So the way we would solve this is by doing an ANOVA. So we compare the weight between these 3 countries, and we can perform the ANOVA, and we can see down here that it is significant. And for example, we could check if we needed rather a Welsh test, if there's any indication of unequal variances. This is not the case. So we can continue with our standard ANOVA, and maybe we can use a post hoc comparison like Tukey's HSD to find out that if you look at these intervals here in the lower right corner, there's actually a significant difference between German and American cars. American cars tend to be heavier than German cars. Japan lies somewhere in the middle between the two, so the difference to the US and Germany is not significant. All right, so this is method 1, just classically working your way through the JMP menus. Now, recently, JMP published an add-in that is called the JMP Assistant. And in the JMP Assistant, you can leverage the power of artificial intelligence to perform the analysis. So on the right side, on the left side, you can see the prompt that I'm going to use the fit Y by X platform to perform an ANOVA of weight versus country, check the assumption of equal variances, perform Tukey HSD post hoc tests. So I'm going to copy this and enter it in the JMP Assistant, and then I just send it to the large language model, which is, by the way, customized version. And this is the result. So you can see that it replies with some explanation, what to look for in the results and the next step. Then it provides the JSL code to actually generate the corresponding analysis, and then you see, just as we had gotten manually the report window with the ANOVA, Germany, Japan, USA. And if I scroll down, you will see the mean comparison. Now, by the way, as all large language models, this doesn't work perfectly, because you can see here that it performed students' t-tests instead of Toki HSD. So if we look at the code, we can see here each pair, and instead it should say all pairs. If I run the code now, then hopefully you see now that we have Toki Kramers HSD. Anyway, so that's version 2, leveraging the power of large language models within JMP with the JMP assistant. Now, let's look at Gemini. So once again, on the left side, you see the Gemini prompt. And for the JMP assistant, the idea was the following. You start with a prompt. The prompt is sent to the large language models that generates JSL. It executes the code, and it gives you some interpretation. Now, in the context of Gemini, Gemini is going to use the prompt to generate Python code. Then the Python code is executed, the results are imported, and then the large language model is leveraged for an interpretation of these results. So here's the prompt: perform a one-way ANOVA of weight by country, check the assumptions of normality and equal variances, perform Toki HSD post hoc test if the ANOVA is significant, create visualizations, report and interpret the results, print the Python code you used to generate the analysis. So just as a remark, this is obviously not the zero knowledge prompt version. This is a lot of statistical knowledge into the prompt. It's just to demonstrate the principal process, how it works. So I switch to Gemini now. So I uploaded the data. Here's the prompt, and I'm sending it now. And just as a side remark, this is the free, fast version of the large language model. So it's not the thinking one, and it will just take a few seconds to give us the results. Here are the box plots. Here's the cuckoo plot checking normality of the response. Then you can see the checking of the assumptions, normality and homogeneity of variances, the ANOVA, the post hoc tests, and the interpretation, followed by the corresponding Python code. So there's nothing to complain about. This is the whole picture. But what we wanted to know is not if that works, because here, actually, if you think about it, the main task is to generate appropriate Python code from the prompt. Python will run without errors, obviously. It will just execute the code, and then there might be some difficulties in the interpretation. But basically, the main task is to translate the prompt into the correct Python code. So, of course, with this prompt, I gave all the details. So it is not a big surprise that this works well. What about if I just use the zero knowledge version, investigate statistically whether weight differs for different levels of country? I did that before so that we don't have to wait for the results. And very much to my surprise, when I saw this the first time, this works perfectly as well. The results are identical to the extended prompt that you saw before. So this is the box plot. We get some descriptive statistics in addition that we didn't get before, with the mean and standard deviation per country. We get the normality and homogeneity of variances check. We get the ANOVA with the interpretation to reject the null hypothesis, the post hoc analysis, and a very clean and well-readable conclusion to interpret the results. So I have to admit, I was impressed the first time I saw this. So for a standard case, an ANOVA without any issues, this simple one-sentence prompt delivered the entire set of results. Now, as we are in the field of hypothesis testing, let's move on to a data set. So I go back to the journal that indeed has some issues. And for this, I used airport delay data. So this is the corresponding data. It contains 180 data points, 25 missing values, 5 huge outliers, and different variances within the group. So if I show you the corresponding ANOVA, it looks like this. And you can see the outliers here in the top. You can see that this leads to heavy non-normality here. And you can see the different variances if you look at the distributions here. So in other words, in this case, a non-parametric test is appropriate. The ANOVA is non-significant, but the Kruskal-Wallis test that you see down here gives a significant result with a p-value of 0.0317. Now, what does Gemini do with this data? Once again, I used the exact same formulation of no statistical knowledge, investigate statistically whether delay differs for different levels of airport. And even more surprising, this worked perfectly as well. So you have the outlier box plot here. You have some violin plots in addition. You have this distribution. You have descriptive statistics. You have the observations and the normality and homogeneity tests that both fail, right? The variants are significantly different, significantly deviate from normal distribution. And then we get the explanation that due to these failures of assumptions, we use the Kruskal-Wallis test instead. And you recognize the p-value here of 0.0317. And it even gives you some Mann-Whitney U tests as a post hoc analysis and a very nicely written conclusion. So despite the fact that this is a non-standard analysis, the one sentence that we used as a prompt without putting any statistics inside gave very nice results in this case. Okay, so for the sake of time, I will just give you a very quick overview of the other areas that I tested. So in the descriptive section, the non-standard case with a big data set, lots of missing values, didn't work well at all. So the standard case was okay, but the non-standard version didn't work at all. The hypothesis tests is the one that I showed you. It worked, in my opinion, at least very well. The linear modeling was okay-ish. It didn't really check assumptions, for example, but overall it was usable. In the classification task, there was a surprise. So for the standard iris data, it worked fine, but not really great. In contrast, for the equity data set that you might know, that has tons of missing values, is a quite large data set, both with categorical and continuous factors, the results were excellent, including data imputation methods, et cetera, et cetera. And finally, the design of experiment is the one that I would like to show you, because there again, I found the result quite surprising. So the standard case I can skip because the result of JMP and Gemini were absolutely identical. So when I ask for a 3-factor response surface model, they just produce the exact same design. Now, as you can see in the prompt, it is impossible to specify a design that you want without statistical knowledge, right? So in this prompt, we have much more detail than in the prompts that we used before. So basically, the information that you need to, for example, create the design in the custom designer, how many factors, that the range of the factors, the interactions that you want in the model, etc. These are obviously information that you have to give the AI, otherwise the comparison is not fair. It can just guess whatever you want. So you can see the prompt here. I want to screen for important factors with an experiment. I have a continuous response, 2 continuous factors, 2 categorical ones. I also have 2 levels that are cannot be combined. So x1 and x2 must not simultaneously exceed 18 for safety reasons. And then I also specified that I can afford at most 15 runs, create the design for the experiment. Here is the data set with the 2 designs side to side. So on the left side, the first 5 columns is the Gemini design, and the second 5 is the design created by JMP. And now, of course, it's hard to assess the difference between the 2, but for this, we can use the Evaluate design platform. So here it is. So this is the prediction profile, same logic. On the left side, this is Gemini, and on the right side is the JMP design. You can see subtle differences, but both look quite okayish, I would say. Down here, you can see the color map on correlation. And once again, the left side overall is a little bit darker, right? So we have a bit more correlation than on the right side. And the probably easiest numbers to interpret are the D efficiencies here. You get 73% on the left side and 87% from JMP. So there's no question the JMP design is better. But I would say the Gemini design is already quite usable. It's not unusable. It's not the best one that we can get. This is what you see on the right side. But it is an okayish design in the situation. Now, if you look at the reasons why it is not optimal, you can see that it didn't handle the constraint perfectly. That is the main reason why it doesn't reach the same D efficiency as the JMP version. All right. So I, with that, go back to my slides. So let's summarize what we saw with some conclusions. Overall, Gemini's performance with sort of stats-free prompts for statistical tasks, in my opinion at least, is surprisingly good. There are some classic mistakes that you will find. The analysis can be sometimes incomplete. So this is something I didn't specify. I repeated every analysis 5 times to see how consistent it would be. It is sometimes inconsistent, will give you different results depending on the run that you perform. And in the interpretation part, in the last part of the output, if you want, you can also find some hallucinations. So for example, it will start hallucinating units. In my experience, the key step to avoid any of these issues is to do the opposite of what I on purpose did here. And this is to make the prompt precise and detailed. So in some sense, to do this, of course, you need some statistical knowledge. So to know the how of statistics is still very useful to get a reliable what from the AI. What are my final thoughts on the human factor? Well, the old rule, garbage in, garbage out, is more relevant than ever. Especially in the context of design of experiments, we all know that domain expertise is absolutely key. So the AI understands the numbers and can create good Python code, but the interpretation of in the context of your problem is, of course, entirely yours. Everything, as always, needs to be fact-checked and validated, because in every response that you get from an AI, there's the danger of hallucination. Causality is something that obviously is completely unknown to an AI. So humans are still the only ones who can truly explain the why. And finally, innovation, AI interpolates from the past, but the true creativity is still uniquely yours. Thank you very much for your attention. I'm looking forward to hearing about your experiences and thoughts about generative AI in the context of statistics, and feel free to reach out on LinkedIn or via email. Thank you.